Hello guys, my name is Patrap here from Civil Engineering Department of Paragon International University. So in this video, I'm going to talk about my term project of M233 Calculus 3. And my topic is about chapter 16, Integration and Vector Fields, 16.5 Surface and Area. So you may know that we define curve in the planes by different ways, such as explicit form y equal to fx, implicit f of x and y equal to 0, parametric vector form R of t equal to f of ti plus g of tj plus h of tk and t from a to b. And we also define surface in the space, like curves. Here we have explicit z equal to f of x and y, implicit f of x and y and z equal to 0. So in this section, we're going to find the surface in parametric vector form, and also we're going to find the area of those surfaces in the space. So the first point, parameterization of surface. And here is the vector function of u and v that define parameterization of the surface in the space. And its definition, it is a continuous vector function that is defined on a region R in the UV plane and one-to-one on the interior of R, where x equal to f of u and v, y equal to g of u and v, and z equal to h of u and v. And u and v are the parameters where u from A to B and v from C to D. And R is the parameter domain. So here the below figures, as you can see, in the UV plane, we have the R region. And when it's parameterization, we get as region of the surface in the space. And vector function of u and v, it defines the surface in space. So example 1, find a parameterization of the cone z equal to square root of x squared plus y squared, and z from 0 to 1. So solution, first, using cylindrical coordinates, so we have x equal to r cosine theta, y equal to r sine theta, z equal to r. So we get parameterization r of r theta equal to r cosine theta I plus r sine theta j plus rk, and r from 0 to 1 and theta from 0 to 2 pi. And example 2. Find a parameterization of the sphere x squared plus y squared plus z squared equal to a squared. So solution, this time we have to use spherical coordinates. So we have x equal to a sine phi cosine theta, y equal to a sine phi sine theta, z equal to a cosine phi. So we get a parameterization of the sphere. R of phi and theta equal to a sine phi cosine theta I plus a sine phi sine theta j plus a cosine phi k. And phi from 0 to pi and theta from 0 to 2 pi. So the second point is about surface area. So in this point, the goal is to find the area of the curved surface by using double integral based on the smooth parameterization. So here the vector function R of u and v. So let's get into the definition. The parameterized surface R of u and v is smooth if partial derivative R by u cross partial derivative R by v is never 0 on the interior of parameter domain, and partial derivative R over u and partial derivative R over v are continuous. So as we can see here, in order to get parameterization of the surface is smooth, we have to find the partial derivative of R over u and over v, and then we have to use the cross product between them. And if the answer is not 0, so it's smooth. And from the definition, they said that partial derivative R over u and over v are non-zero, so they determine the plane tangent to the surface. So let's look at the figures here. So in the UV plane, we have the origin, and in the origin, we can pick a very small rectangle. So here, the rectangle, And when it's parameterization, so in the space, we can get the surface in the space, so S region. So the yellow rectangle will be on the region S also. So as you can count in the yellow rectangle, we can find the area of this surface S. So let's look at the yellow rectangle. So as from the previous point, we said that the surface is smooth if partial derivative R over U and over V cross product between them is not zero. So we assume that this yellow rectangle of the S surface is not, is smooth. So if it's smooth, we can say that partial derivative RU and RV cross, so it's not zero. And as you can see here, the yellow rectangle of the surface, we can assume it is a parallelogram. So here, as you can see, it is a parallelogram. So we have to use the formula, the area of the parallelogram. So we get absolute value of the chain of U times partial derivative R over U cross the chain of V times partial derivative R over V. So it equal to absolute value of partial derivative R over U cross R over V and time absolute time chain of U and time the chain of V. So we get the area of the parallelogram. So this is the yellow rectangle, a small yellow rectangle. So by sum of each partition over the region R. So we mean that we have to sum the yellow rectangle over the region R. So by the sum we get this the sum of the area of the parallelogram. So we get the area of the smooth surface of U and V. So we get area equal to double integral C to D, A to B. And here is the area of the parallelogram. So it's actually the area of the smooth surface by using double integral. And also a surface area differential for parameterized surface. We can actually abbreviate the formula of the area of the smooth surface by using d sigma equal to absolute value of partial derivative R over U cross R over V du dv. So we get this formula. So example, find the surface area of the cone z equal to z equal to square root of x squared plus y squared, z from 0 to 1. So the answer, as you can see, this is the parameterization of the cone, and r from 0 to 1 and theta from 0 to 2 pi. So we have to find the partial derivative of r over radius r and over theta. And then we have to use the cross product between the partial derivative. So r over r cross r over theta. So we get square root of 2 times r. So using the formula from the previous definition. So the area of the surface. So A, double integral 0 to 1, 0 to 2 pi. So here, the absolute value. So d theta and dr. So we get the answer square root of 2 and 10 pi. And here is the third point. We can also find the area of the surface of the implicit surface. So here the implicit surface f of x and y equal to c, and c is constant. So by using these figures, we can actually find the formula of the area of the implicit surface. So gradient f scalar vector p equal to gradient f scalar vector k equal to fz, and fz is never 0. So as you can see here, because vector p parallel to vector z in the space, and vector p perpendicular to this region R, and region R is actually this surface in the space. And they define the parameters u and v by u equal to x and v equal to y, then then z equal to h of u and v, and r of u and v equal to ui plus vj plus h of u and vk. And then calculating the partial derivative of r, we find so r over u equal to I plus partial derivative h of partial derivative h over u k and rv equal to j plus partial derivative of h over v k. And we also know that a partial derivative h over u and over v. So here, minus fx over fz and minus fy over fz. So we have to substitute this second equation into the first equation. So we get u equal to I minus fx over fzk and rv equal to j minus fy over fzk. And then we have to use the cross product between the partial derivative r over u and r over v. So we get here gradient f over fz. And fz, as you can look at the previous slide, we know that it's equals to gradient f scalar p. So we get this answer. And we have to substitute. So d sigma equal to absolute value of partial derivative r over u cross r over v times the chain of u times the chain of v. So it equals to absolute value of gradient f over absolute value of gradient f scalar p dx dy. So we get the formula surface area of an implicit surface as equal to double integral over the region R, absolute value of gradient f over absolute value of gradient f scalar p dA, where vector p equal to Ez of k and is normal to region R. And gradient f scalar p is never zero. So there you go, the formula of the surface area of an implicit surface. So example, find the area of the surface cut from the bottom of the paraboloid x squared plus y squared minus z equal to 0 by the plane z equal to 4. So the answer, we have to use the formula of the implicit surface. So gradient f equal to 2xi plus 2yj minus 1k, because we just have to derivative this paraboloid. And then we have to find the absolute value of gradient f and also gradient f scalar p. And we have to find the absolute value of it. So it equal to 1. Then using the area of implicit surface formula. So we get here pi over 6 times 17 square root of 17 minus 1. So that's the answer. And we also can find another formula, surface area of a graph z equal to f of x and y. And here is the formula, area equal to double integral over region R, square root of partial derivative f over x squared plus partial derivative f over y squared plus 1 dx dy. So here, as you can see, this is how we get this above formula. So we have x equal to u, y is equal to v, and z equal to f of u and v. And here is the vector function of u and v equal to ui plus vj plus f of u and vk. And then we have to find the partial derivative r over u and r over v. And then we have to use the cross product between them and then find the absolute value. So we get here square root of partial derivative f over u squared plus partial derivative f over v squared and plus 1. And then substitute u and v. So we get d sigma equal to absolute value, d sigma equal to square root partial derivative f over x squared plus partial derivative f over y squared plus 1 dx dy. And that's how we get the formula of the surface area of a graph z equal to f of x and y. So let's do an example. So application, find the area of the cut from the sphere x squared plus y squared plus z squared equal to 2, while the cone z equal to square root of x squared plus y squared. So the solution by using the formula of the implicit surface, because as you can see here, this is an implicit surface. So the area, and then we have to find the gradient f. So we have to derivative the sphere here. And then we have to find the gradient f scalar p. So here we have gradient f and gradient f scalar p. And then find the absolute value of gradient f. So we get 2 times square root of 2. And also x squared plus y squared equals z squared. So we have to find the region of r and theta from the sphere. So r from 0 to 1 and theta from 0 to 2 pi. Then just using double integral of the area of an implicit surface. So the answer here, 2 pi times 2 minus square root of 2. So that's the answer of this exercise. And that's the end of our video. So thank you for listening and have a good day.